Alright class, in today's video we are going to be beginning our second unit of the school year. We're going to be looking at our kinematic equations as well as two-dimensional motion now. So what we're going to focus in on today is going to be how we get these three kinematic equations we'll be using the rest of our unit. So up until this point we've seen two-minute equations dealing with average velocity and average acceleration. So we've been able to describe a number of different scenarios using those two equations, but there are some limitations with those two that don't allow us to analyze every single thing. So what we're going to be doing is expanding kind of our toolbox here by adding in these three additional equations that are going to allow us to describe more cases of motion. And what we're going to be specifically focusing on here is going to be motion that has a constant acceleration. So our value for A, always going to be the same, it's not going to be changing. We're dealing with a situation with a constant acceleration. So these three equations, we refer to them as our kinematic equations, and we'll derive them in just a second here. But when we think about this term kinematics, all it means is we're describing motion without discussing forces. So forces will come in our next unit, Unit 3, but for right now we're going to still describe motion, but we're not going to talk about forces at the moment. So in looking at our kinematic equations, we're going to walk through today how physicists were able to come up with them. And the first one is actually an equation you guys have already seen before. So if we think back to our equation for acceleration, we said acceleration, and in this case we're dealing with our average acceleration, is equal to our change in velocity over our change in time. Now, because we're only dealing with situations that have a constant acceleration, our average acceleration is just going to be the same value throughout. So we're going to say, because our acceleration is constant, so that we can just replace our average acceleration. It can be the same thing as just our acceleration at any given moment, which we'll write as A. So from here we're going to say A is equal to, remember, anytime we have a change in velocity, we have velocity final minus velocity initial. That's going to be divided by T final minus T initial. Now, one thing you guys probably picked up on last unit when we were using this equation is our initial time is pretty much almost always going to be 0. So we start counting 0, we move forward. We really never have situations with negative time. Initial time always starts at 0. So what we can do is plug that 0 in and rewrite our equation as A is equal to V final minus V initial over T minus 0. From there, what I'm going to do, now that I've done that subtraction on the denominator, I'm going to try to isolate or get my variable v all by itself. So to do that, I'm going to multiply t to both sides. So you're going to have v minus v sub 0 is going to equal a times t. Last thing, again, I want my final velocity all by itself. So I'm going to add our v initial to both sides here. So the equation we're going to have is going to be final velocity is equal to initial velocity plus AT. So again, we'll call this our first kinematic equation here, and all it is just a rewriting of our equation for average acceleration. So again, what we have here is our final velocity is going to be equal to our initial velocity plus our acceleration times time. So this will be our kinematic equation number 1. our second kinematic equation that we're going to get here, instead of deriving it from our equation for acceleration, we're going to derive it from our equation for average velocity. So before we said average velocity was equal to our change in x, our change in position, over our change in time. And what we're going to do here is we're going to, instead of writing in terms of average velocity, we're going to manipulate this so we have change in x is equal to something. So we're going to multiply both sides by delta t here. And we have change in x is equal to our average velocity times our change in time, or delta t here. So what we're going to do in order to come up with this second kinematic equation is we need to figure out things that we can plug in for average velocity, is we can plug in for our change in time. So first thing is, when we think about average velocity, one thing that you guys learned back in math was to take an average. What you can do is you can you can add up a set of numbers and then divide by however many numbers you had. So if we have quantities of initial velocity and final velocity, we can find the average between our initial velocity and our final by again adding them up, and then because we have two terms, we're going to divide by 2. So what this equation does is it tells us the average between our initial and final velocity. So this step we have here, v average is equal to v0 plus v divided by 2. It's going to come in handy in just a little bit here. But before we do that, we're actually going to revisit that equation we had for acceleration is equal to delta v over delta t. So just as what we set up here, because these kinematic equations only apply when our acceleration is a constant, we can rewrite our average velocity as just, we can rewrite our average acceleration as just a for acceleration. In this case, what we're going to do is we are going to instead isolate our delta t, our change in time. And what we get here is by solving for our delta t, we have change in velocity over our acceleration. And we can finally, we'll take our change in velocity. We know anytime we have a change, we have final minus initial. So we're going to have final velocity minus initial velocity divided by a. So guys, the reason why we did all this work on the right side here is that I now have something I can plug in for our average velocity. And I have something I can now plug in for our delta t. So what this looks like is we can rewrite our change in position is going to be equal to v initial plus v over 2. That's going to be multiplied with what we have for our change in time, which we're now going to replace by v minus v initial over a. So in multiplying these two fractions with each other, we can rewrite this as delta x is equal to, and in our numerator up top, we're going to have v initial plus v times the quantity v minus v initial. And then the 2a at the bottom gets multiplied by each other to form a new denominator. So to simplify this a bit more, we're going to have to multiply our numerator, and we're going to use kind of the FOIL method you guys learned from algebra, or just any other way you guys learned how to multiply these sets of sums here. So what that looks like here is our denominator is going to stay the exact same of 2a, and now that v initial is going to be multiplied with our v here, so that first FOIL, so we have v initial times v. The next thing we have is v initial is going to be multiplied by the second v initial on the right side. Add that to v initial times negative v initial. It gives us a negative v initial squared. No, excuse me, that squared should be on the inside of our parentheses. Next up, we're going to be looking at our first v is going to multiply by our second v to give us plus v squared. And then lastly, we have our second v multiplied by our second negative v initial. This is going to give us a negative v initial times v. So again, we're going to want to simplify this just a little bit more here. So first thing I'm going to say is that our v initial times v is going to cancel out with our negative v initial times v. We're going to add those two together. And I can rewrite our equation here as delta x is equal to v squared minus v initial squared over 2a. Again, we are very close here to coming up with this second equation. I'm going to multiply both sides by 2a. We'll bring this now up here. And we are going to say that v squared minus v initial squared is equal to 2a delta x. From there, we're going to add v initial squared to both sides, giving us v squared is equal to v initial squared plus 2a delta x. The very last thing we're going to do to get our equation is we know that delta x just means final minus initial, which is going to give us v squared is equal to v initial squared plus 2 times a times the quantity x final minus x initial. So again, after all that work, we finally have our second kinematic equation here. This will be our number 2. Again, we have our final velocity squared is equal to initial velocity squared plus 2 times our acceleration times the quantity final position minus initial position. So those are the first two equations. We have one final one, and it's actually something that we get from a velocity versus time graph. So in our velocity versus time graph, we know that our acceleration is a constant. So what this means is that our acceleration is going to be the slope of this v versus t graph. So that means we're going to have a constant slope. So that might look like something like this here. So in looking at this velocity versus time graph, we see that the slope tells us our acceleration, whereas our area underneath our curve is going to tell us our change in x. So our change in x is equal to area under our curve. And we'll say that this point along our y-axis here, we start off, this is going to be our initial velocity. And this is the velocity we are at time is equal to 0. And then what we have here is a y value of our final velocity. So what we're looking here for our area underneath our curve is going to be a couple of things. So first thing we have is, as we look at this area we want to find in here, let's say we're going up to some time t, we want to be able to find the area of our shape in here. So to do that, what I can do is break this off into a rectangle and a triangle. So looking at the area of our rectangle, our area is going to be length times width, which in this case we're going to have a width here of t. Our height is going to be v initial, so that area is going to be v initial times t. As we take a look at the area of our triangle, we're going to have 1/2 base times height, where we can say that the height of our triangle can be this difference of v minus v initial. Same thing, we can call this our delta v here. And our base is going to be t. So we're going to say area is going to be equal to 1/2 times our base of t times our height of change in velocity. So our total area under the curve, which we can say is delta x, is equal to v initial t plus 1/2 times t times delta v. So we're very close here, guys, in coming up with our equation, but typically we don't have kind of change of velocity delta v in our equation, and we are instead going to want to rewrite that in terms of an acceleration. So just as we've said before, we had our acceleration is equal to change in velocity over change in time. Again, because we're going to say t initial is equal to 0, what we can do is say that delta t is just going to be equal to our final t minus 0, which is going to give us just t. So we can manipulate this equation a little bit, multiply both sides by delta t, and we're going to get our change in velocity is equal to a delta t. This is what we are going to want to then plug into our value here for delta v. So we get delta x is equal to v initial times t plus 1/2 times t times what we plug in now is going to be a delta t, but remember we said delta t was just t minus 0 or t. From there we can say delta x is equal to v initial t plus 1/2 at squared and then finally our change in x is going to be our x final minus our x initial, and we're going to want to solve this one for our final position. So we're going to add our initial position to both sides, we get our final position is equal to our initial position plus v sub 0t plus now 1/2 at squared. So this is going to be our third and final kinematic equation that we're going to be making use of over the next few days. So what we have here is, we'll say that our final position is going to be x. Our x sub 0 is going to be our initial position. Our v sub 0 is going to be our initial velocity. Our t here is going to be our time. Finally, a is going to be our acceleration.